22 kilometers of rise, a base 600 kilometers wide, a slope so shallow it barely qualifies as a hill. You could stand on the biggest mountain and never know it. Your boots touch dust that looks like every other patch of dust you have crossed for the last 3 days. The ground reads flat. Your instruments say otherwise. Nothing under your feet agrees with the map in your visor. This is Olympus Mons, the tallest volcano in the solar system. It climbs almost 3 Everests stacked on top of each other. Yet standing on its summit feels like standing on a parking lot. The scale printed on your mission briefing does not match anything your body reports back to you. You expected wind-scoured cliffs. You expected a horizon that drops away beneath your boots. Instead, the dust just continues. The same shade of rust brown rolling out in every direction, broken only by the occasional boulder kicked loose by some ancient impact. The mountain's height comes from Mars itself. Low gravity lets magma pile up instead of collapsing under its own weight. On Earth, a volcano of this heavy would sink into the crust long before reaching such height. Mars never applies that brake. Layer after layer of lava stacks without slumping, without buckling, without any of the sagging that limits Hawaiian volcanoes to a fraction of this scale. Mauna, the tallest volcano on Earth, measured from its ocean floor base, tops out at roughly 10 kilometers. Olympus Mons more than doubles that figure, and it does so on a planet with barely a third of Earth's surface gravity holding it down. The result spreads sideways as much as it grows upward. A structure that tall needs a base wide enough to support it, and that base stretches wider than the entire state of Arizona. That width is the trap. Spread 22 kilometers of elevation across 600 kilometers of ground, and the numbers flatten out fast. The average slope drops to somewhere between 2 and 5 degrees. Most wheelchair ramps are steeper than that. Airport jet bridges tilt more sharply than the surface of the tallest peak in the solar system. Your legs, your ears, your inner sense of up and down, none of them evolved to register a grade that gentle as a mountain. They register it as flat ground, because that is exactly what a 5-degree incline feels like to a walking body. The organ responsible for balance sits inside your inner ear, a set of fluid-filled canals that detect tilt and rotation. That system calibrated itself on millions of years of Earth terrain, where 5 degrees barely registers against noise from uneven rocks and loose soil. A 5-degree slope stretched across 300 kilometers produces no signal that fluid-filled canal was ever built to notice. Muscles in your calves and thighs, the ones that should ache differently on an incline than on flat ground, report nothing unusual either. The strain of a 5-degree grade blends into the ordinary fatigue of a long walk in a pressurized suit, indistinguishable from exhaustion on any flat plane back on Earth. Plant your flag. Look around. Every direction shows the same gray horizon. No peak rises above you. No valley drops below. The floor just keeps going, mile after mile, indistinguishable from where you started. You climb higher, hoping altitude will fix what your legs cannot feel. On Earth, pilots flying above 20 kilometers report the horizon curving, the black of space creeping into the edges of the sky. That benchmark comes from real flights. In 2020, U-2 and SR-71 pilots comparing high-altitude photographs confirmed that Earth's curve becomes visible to the naked eye once you cross roughly that same 22-kilometer mark. The obvious move is to expect the same trick here, standing at the same altitude on a taller peak. Reach the exact elevation where Earth reveals its shape and expect Mars to do the same trick at the summit of its tallest structure. It fails immediately. Mars is smaller than Earth. Its radius runs barely half of Earth's, which means its horizon curves away far faster and much closer to your feet. Stand at any height on this planet, and the ground drops out of sight sooner than instinct expects. The math works against you before you even leave the ground. A smaller radius means less distance to the true edge of sight, and less distance to the edge of sight means the volcano's own slope gets in the way before curvature or edge ever comes into view. The horizon should have been your proof. Instead, it disappears behind a hill you cannot perceive as a hill. Your eyes run out of tools before your legs do. Push forward anyway, and distance becomes its own enemy. The rim of the summit caldera sits roughly 300 kilometers from the base. Walking that distance without stopping takes something close to 60 straight hours. No human sustains that pace. Rest breaks stretch the trip into bays, and every one of those days repeats the same view: flat gray ground in front, flat gray ground behind. A support crew back at base camp starts counting down suit oxygen instead of counting up elevation gained, because nothing about the terrain gives them a landmark to track against. Distance swallows the climb before slope ever gets the chance to. Think about what 60 hours of unbroken walking actually costs a human body. Blisters form inside pressurized boots within the first day, aggravated by a suit that never lets skin breathe or cool the way it would in open air. Joints designed for Earth's gravity absorb less shock in Mars' gravity, which sounds like relief until repeated impact starts loosening cartilage in ways engineers still study on the International Space Station. Every single one of those hours passes across ground that looks identical to the hour before it, denying the climber the psychological reward that usually comes with visible progress up a slope. Thin air removes the last cue your body might have used. On Earth, haze thickens near sea level and thins with altitude, giving climbers a visual signal that they have gained height. Clouds stack below a true peak, marking the line between summit and sky. Mars strips that away almost entirely. Its atmosphere sits at roughly 1% of Earth's pressure, too thin to hold the moisture or dust layering that creates visible elevation bands. No haze thickens at the base. No cloud deck marks the summit. The one visual trick your brain relies on to judge height from a distance simply has nothing to work with here. Your senses run out of evidence at every layer, one after another. So the eyes fail on slope, the horizon fails on radius, the legs fail on distance, the air fails on haze. Each gap opens exactly where the last one closed, and by the time you reach the flag, every physical signal a human body uses to detect a mountain has already been silenced by a different piece of Martian physics. Nothing about walking harder or climbing faster changes that outcome. A stronger climber crosses the distance sooner and simply confirms the same flat ground faster. Better lungs do not restore missing haze. Sharper eyesight does not undo a horizon that curves away too soon. Training harder on Earth beforehand, the way astronauts train for microgravity in pools and centrifuges, does nothing to prepare an inner ear for a slope with no detectable tilt. The instinct to trust your own body, the same instinct that works on every mountain on Earth, becomes the exact reason you cannot detect this one. The fix does not live in muscle or eyesight at all. Orbital radar solved what boots on the ground never could. Spacecraft mapping Mars from above measure elevation directly, bouncing signals off the surface and timing the return to build a picture no climber could ever construct from inside the terrain. That data revealed Olympus Mons for what it is long before any lander touched its base. The instrument does not walk the slope or squint at a horizon. It measures height the same way regardless of how gentle or steep the ground feels underfoot, which is precisely the advantage a human body can never match. Instruments see scale. Bodies only feel grade. Picture the mountain from orbit instead of from the surface, and the entire shape snaps into focus. A shield volcano the width of a small country rises out of the Martian plains, its summit lost in the thin haze of upper atmosphere, calderas nested like scars from a dozen separate eruptions. From 200 kilometers up, satellite sensors capture in seconds what would take a walking climber a week to traverse and still fail to comprehend.
That single jump from a boot pressed into gray dust to a satellite orbiting far overhead is the only jump that reveals what this planet actually built. Radar altimeters used to map Olympus Mons work by sending a pulse toward the surface and timing how long the reflection takes to return. A slope too gentle for a boot to feel registers instantly in that timing difference because the instrument measures distance in fractions of a second rather than through muscle strain or inner ear tilt. Repeat that pulse thousands of times across an orbital pass, and the satellite builds an elevation map accurate to a few meters, resolving a structure that no single climber walking the surface could ever piece together from memory of a week-long trek across identical gray dust. Zoom back down to the caldera floor, and the illusion returns instantly. Cracked rock, shallow slopes, a horizon that looks ordinary. The mountain hides again the moment a human stands on it. That is the mechanism working exactly as physics designed it to work. Every element that makes Olympus Mons the tallest peak in the solar system is the same element that keeps it invisible to the body standing on top of it. Low gravity built the height by letting lava pile without collapsing. That same low gravity spread the base wide enough to erase the slope. A smaller planetary radius that let the volcano grow also curves the horizon away before any climber can use it as a reference. Thin air that failed to compress the lava into a smaller footprint also stripped away the haze that would have signaled elevation. Scale and invisibility were never separate outcomes here. They are the same physical event viewed from two different distances. Consider what a similar structure would look like if it existed on Earth. A mountain 22 kilometers tall would punch through the stratosphere, cold enough at its summit to freeze exposed skin in seconds, and thin enough in air pressure to require a full pressure suit long before the peak. No such mountain survives on Earth because Earth's stronger gravity and thicker crust crack and collapse anything that tries to grow past roughly 10 kilometers. Mars simply never enforces that limit. The absence of a ceiling on height is exactly why a shield volcano here can outgrow every mountain a human evolved to recognize, and exactly why nothing in human perception evolved to handle the result. Ancient eruptions built this structure slowly over hundreds of millions of years, one thin sheet of lava at a time. Each individual flow may have added only a few meters to the surface, spreading outward across the plain before cooling into solid rock. Repeat that process across geological time, and the mountain grows in exactly the direction human senses are worst at detecting, outward, not upward. A climber walking across any single one of those ancient flows feels nothing more dramatic than a slight change in the color of the dust underfoot. Multiply that unremarkable sensation by thousands of individual flows stacked over millions of years, and the sum becomes the largest volcanic structure known in the solar system, invisible one flow at a time, and undeniable only when measured as a whole. Even the summit caldera, the collapsed crater at the very top, offers no relief from the illusion. Multiple overlapping calderas mark the peak, evidence of repeated collapses as magma drained and refilled the chamber below across different eruptive periods. From orbit, those overlapping craters look dramatic, scarred and layered like rings on a cut tree trunk. Standing at the rim of one, a climber sees only a shallow depression a few hundred meters deep, cut into a landscape that already reads as flat. The single feature on this mountain steep enough to register as terrain barely qualifies as a dent against the scale of everything surrounding it. That is not an accident of perception, it is the direct result of the numbers. A 5-degree slope will always read as flat ground on a walking body no matter which planet it sits on. A 600-kilometer base will always place the true edge of the structure beyond any line of sight a human eye can trace unaided. A horizon curving faster on a smaller world will always defeat the old trick of climbing higher to see farther. None of these are quirks specific to Mars. They are constants that apply to any tall, shallow structure large enough to outscale the body measuring it. Compare this to what a climber feels on Denali or Kilimanjaro. Those peaks rise steeply enough that leg muscles burn differently within the first hour, that the air visibly thins, that clouds sit below the summit like a floor made of cotton. Olympus Mons denies every one of those cues at once, not because it is smaller or gentler than those mountains, but because its enormous scale stretched the same warning signs so thin across so much distance that no human sense can gather enough of them in one place to notice a trend. Future missions will face the same wall. Landers scouting Olympus Mons for future crewed exploration already rely entirely on orbital elevation data rather than surface reconnaissance, because no rover-mounted camera at ground level can register the mountain's true shape from inside its own slope. Even a future human mission standing at the rim of the summit caldera will look out at the same flat gray plain that greeted every earlier probe. Radar and satellites will keep mapping the shape from above. That will never change what the astronaut standing at the summit sees with unaided eyes. The mountain will always be measurable. It will never be visible from its own surface. That gap between the two is permanent, built into the geometry itself, and no future spacesuit, no future sets of eyes will ever close it.